Hi everyone, I'm Kibom Han, the teaching assistant of this course. Today I would like to talk about the recent advances in rendering, especially about Monte Carlo noise reduction.
Firstly, I'll go over some concepts we dealt in class for review. The basic principle of many light transport algorithms rely on this rendering equation. This equation provides a somewhat iterative way of how to calculate the outgoing radiance based on the emitting radiance and reflected ones. Here, the complex part is the integral, where we should consider all incoming radiances and the material property to calculate the reflected radiance. Since we have a wide variety of lighting and materials, the integration is hard to be computed. Monte Carlo ray tracing overcomes the problem by applying Monte Carlo integration. We take numerous samples based on the certain sampling PDF and get the weighted sum of all samples calculations. This relies on the nature that Monte Carlo integration is unbiased, which means it'll eventually converge to a correct value. However, to get a good approximation, we require a lot of samples and a good PDF that represents the integrand. As you can see from this figure, shooting less samples leads to noisy results while rendering in a short time. But on the other hand, shooting a lot of samples leads to a clean render results, but with a long time consumption.
And so now our goal is to reduce the noise and to render a clean image within a short time budget. And firstly, I would like to deliver various methods that can reduce noise in path space, which means reducing noise during rendering. The first method is called Metropolis Light Transport, or MOT, and this uses an advanced sampling technique called Metropolis hasting algorithm to generate valid samples. So this is how it works. So suppose that we have eventually found a valid light path that reaches the light source. And after that, we don't sample a new path, we just simply mutate this valid path by jittering the vertices of the path. By doing so, we can easily generate more valid light samples, which will result in reducing the noise of the rendered result. So in this case, we can see that by mutating, we can find more valid light paths which can go through this door, which has the light source at the other side. And as we can see, the left result using MLT is showing less noise than the right one, which is using a simple path tracing. There is also bidirectional path tracing, which also tries to find the valid path easier. So in this case, we shoot rays from both sources, first from the eye point and another from the light source. And after certain bounces, we connect each path to create a valid path from the eye to light source. This is why it is called a bidirectional path tracing. And by doing so, we can easily connect the eye and the light. And as you can see from this results, it is very beneficial for complex geometries, materials, and with indirect lightings.
While the two methods were unbiased sampling methods, they are also biased methods which allows faster convergence but with a consistent bias. One is irradiance caching, which caches the irradiance of the visible points and interpolate them when rendering. The intuition here is that most indirect lightings are smooth, which might require only a sparse computation to get a plausible result. And this is how you interpolate the irradiances using gradients. Another biased approach is photon mapping. Unlike before, we save information of n-pass photons shot from the light source. And then we use the k-nearest photons to estimate the radiance of the curve point. Here we can see the result of rendering with the photon map on the left, where the photon map can be visualized as the right here. Path guiding guides light samples to a certain position or direction that is assumed to reduce the noise. During rendering, we can use a certain metric that reflects the noise levels like the radiance. So in this case, we would like the light samples to have a high radiance, that we can give higher probability to the direction that has higher radiance, like the figure here. Suppose we guide the samples with direction, and we can express the map as the hemisphere here. With this map, we can progressively guide the samples to the desired direction that can reduce the noise. Various structures can be used to model the sampling map. This work shows that using Gaussian mixture model outperforms other grid-like structures when representing sampling maps, and also when rendering, which shows more plausible rendering results. There is another approach called path space filtering or path reuse. Suppose we already shot some samples and then we want to shoot another one. Then, instead of tracing the sample till the end, we just used a weighted sum of the nearby samples to calculate the radiance, which is similar to filtering methods. And this is also analogous to reusing because each sample path can be viewed as reusing the suffix of the existing path. The path space filtering can easily cope with indirect lighting, as we can see from the various combinations of light paths. And this also leads to noise reduction, like the figure here. And now, let's go over to some image space methods. Since the rendering result is an image, we can easily imagine applying image denoising methods, which is efficient and less complex. So while path space methods before dealt on n-dimensional space, here we can only consider a 2D space, an image. General image denoising algorithms like non-local means filters, cross-bilateral filters, and Blanc matching 3D filters were applied to reduce the noise of the rendered images. Each method has their own way to estimate the filter weights, and that'll be applied to the noisy image. But unlike general image denoising, the filter weights are not solely determined based on RGB colors. During rendering, we can obtain useful geometric cues, we call it G-buffers, which is consisted of albedo, normal, and depths. In our case, these features are also used to determine the filter weights, like the equation here. So since now we have reviewed some classic methods, now let's move to recent learning-based methods, which most of you will be interested in. I hope that you guys are familiar with concepts of deep learning, convolutional networks, adversarial training, self-attention transformers, neural radiance fields, and so on. And here we will cover image space, sample space, path space, and post-post processing methods using deep learning for rendering. As deep learning got popular, various neural networks and training methods have been introduced to enhance tasks on image domain. Image denoising using deep learning reduces human design biases of traditional filters. And when using deep learning for Monte Carlo noise reduction, we train a neural network to predict the clean image from the input noisy image and the auxiliary features. The pioneering work applying deep learning used MLP to estimate filter parameters for cross-bilateral filters. It have used more than 20 channels of inputs and thousands of images for training. And this work surpassed most classic approaches for Monte Carlo noise reduction. The next work gave a more flexible approach where the neural network is trained to estimate the filter weight itself, not the parameters. And this work also showed that estimating a kernel leads to a more robust training compared to directly estimating the pixel RGB colors, as you can see from the figure. Here we can see that the green kernel predicting networks show better convergence, better stable convergence compared to directly estimating the images, like the blue one. This is because estimating weights has less search space than estimating a radiance itself, which makes it more easy for training. Also, this work decomposed the image into diffuse and specular image and trained the denoising network for each images. The reason of this decomposition is that we want denoising networks to focus on two different types of noise, which comes from different types of light transport. Here, the diffuse lightings are geometry dependent, smooth, and has low range. But on the other hand, the specular lighting tends to be view dependent and to have higher range. And from this figure we can see that this work called KPCN shows better performance on these small details compared to previous methods. And nowadays, kernel prediction and decomposition became a de facto on our field. However, there is a way to achieve par or better results using direct image prediction instead of kernel prediction. This work utilized adversarial training to make the denoising network to directly estimate the denoised pixels. They jointly train the denoising network and the critting network. The critting network guesses whether the input image is clean or denoised, while the denoising network is trained to fool the critting network. Such training process successfully regularized the denoising network to reconstruct better details than before. As you can see, the specular details and the texture details are well reconstructed than the other models. Moreover, more recent work used self-attention mechanism to provide strong guidance of auxiliary features for denoising. Well, shortly, the self-attention mechanisms on each block allows to learn global contribution between the inputs, in this case, the noisy image and the auxiliary features. And these will be represented as the blue boxes here. If we see these blue attention maps close, we can see that the attention map highlights the parts where the auxiliary features have high correspondence with the query red pixel. By doing so, with a lot of computational power, this method achieved better results than KPCN and the adversarial work for these fine specular details and the textures. Now we have talked about learning-based methods on image space. And let's move to sample space and path space methods. The motivation of this expansion is because there are effects that can be only expressed in sample space and path space. For instance, generating blurring effects like depth of fields and motion blur are generated by jittering samples. So we need methods to work on sample space to successfully remove the noise while maintaining these effects. To work on sample space, one work uses sample-wise splatting kernel, which turn the intuition of the kernel to the opposite. The conventional kernels usually gather pixels or samples of nearby based on their assigned weights. And this is analogous for a denoising pixel, asking, is the ith sample of my jth neighbor an outlier? But on the other hand, splatting kernel comes with an intuition where a noisy pixels or samples contribute to the target pixel with its own weight. And this is analogous for the noisy pixel or the noisy sample asking, am I an outlier to my certain neighbor? And this concept is more intuitive to deal with samples, and also it is permutation invariant. And also empirically, empirical results show that we can achieve larger kernel while using smaller networks compared to using gather kernels. And by this, we can reduce the memory overhead. And this is the neural network that estimates the splatting kernel weights. And here we can see that the sample-based Monte Carlo denoising, or SBMC, shows better denoising on general cases and on sample-wise effects. And for the next work, we will talk about path space. So, the path space refers to features from each bounce of the light, where it can contain multi-bounce features that are helpful for reconstructing complex lighting details. But however, numerous bounces makes the data too high dimensional, making hard for the neural network to be trained optimally. Here in this case, the input will have at least 74 channels per sample, which is a lot for the neural network to be trained to. In order to effectively utilize the path space features, this work introduces a manifold learning that embeds path features into a low-dimensional space. And then, the embedded path features are fed to the denoising network along with other inputs. Of manifold learning, they used contrastive learning to train the path embedding network, which clusters the path with a similar pixel radiance together and repels path with different pixel radiances. And here, we can see that the paths contributing to the same pixel are embedded into local areas using manifold learning. Using the manifold learning, the work could better reconstruct complex lighting effects and fine details. And here, I'll introduce another interesting approach which uses neuroradiance fields for path space denoising. So, the core of ray tracing is to solve the rendering equation here. What if we can train a neural network to predict the reflected radiance instead of integrating or computing samples? Suppose we have such a neural network that can estimate the reflected radiance. Then, the training of the neural network can be viewed as caching the radiances implicitly to the neural network. And also, estimating the radiance using the neural network can be viewed as the neural network implicitly interpolating the cached radiances, and this is why the work is called neural radiance caching. However, the problem is that we don't have the ground truth. Obtaining the ground truth for all radiances is very time-consuming. So, this work provides a self-training approach, which is to minimize the loss between the calculated and the estimated radiances. As in the figure, we can estimate the radiance from Y4 using neural radiance cache and calculate the radiance from Y3, Y2, and Y1 based on the radiance out of Y4. And these are calculated radiances, a blue one. And we can also directly estimate the outgoing radiances of Y3, Y2, and Y1 using neural radiance cache, which will be the estimated radiances, the red one. And this work trained to minimize the differences between these two as the loss equation here. And then when rendering, it simply estimates the radiance using the neural radiance cache as the x2 here. Using the neural radiance cache, we can get a more valid radiances, which gives a more brighter and noiseless images. And note that the remaining noise still comes from the sampling probability of samples where the cache will be calculated. And we can remove the remaining noise using existing image space denoisers and get a more reliable result. Now, let's move on to path guiding with learning-based methods. And before that, let's talk about reinforcement learning. The reinforcement learning has a different framework from common supervised learning methods. Here we want to train an agent to find a good policy which gives an action that can maximize the reward on a certain environment. And for rendering, the agent will be a guiding process, and then the environment will be the rendering process based on the guided samples during action. For the path guiding using reinforcement learning, this work declared a QNet, which estimates the policy. In our case, the policy of the QNet is to manipulate the sampling map based on the given inputs. So for the action, on each sampling iteration, the QNet's action is to refine or resample the sampling map, as the figures here. And then the RNet here is trained to evaluate the image. This RNet is simply a denoising network that denoise an image sampled using the sampling map. Then the loss of the denoised image will be used as a reward. So by jointly training the QNet and the RNet to maximize the reward, this work expects the QNet to provide an effective sampling maps and RNet to effectively denoise the rendered result. And this result shows that the sampling map from QNet is closer to the reference compared to other methods, leading to better denoising performance. We can also apply implicit neural representation for path guiding. This work trained an implicit neural representation to encode the parameters of mixture models that can represent sampling probabilities throughout the 3D space. And here we can see that this simple idea can enhance performance for path guiding. Now this is the last topic we're going to talk about, and let's talk about post-processing the denoisers, which is somehow a new concept of work. Previously, I have said that learning-based denoisers are free from human design biases. However, they are still biased to datasets, which cannot fully cover the noise distribution for training, and therefore the performance of the denoisers cannot be consistent throughout the noise levels, or SPP. The orange and the brown line of the figure shows that the trained denoiser KPCN and self-attention shows worse performance than path tracing on moderate sample numbers. To overcome such a problem, this work uses a concept of combining biased and unbiased estimate. And let's talk about the basic principles here. So we have two inputs. One is a path traced input, which is a noisy but unbiased. Another one is a denoise result, which is less noisy but biased. Using two inputs, the James Stein estimator can provide a better solution that has a least error than the other two by combining using the equation here. The intuition comes from balancing the bias and the variance of the two results. For example, MSE loss can be represented as a sum of squared bias and the variance. We normally think that reducing the bias will lead to lower loss, but reducing the variance is also important. So, the James Stein estimator reduces the variance efficiently while leaving space on bias term, resulting to a lower error rate. This figure can show you a visual example. The gray points are uniformly sampled on the radius mentioned here with a center of 1.1.1, and the red points are results of James Stein combiner of gray points and the points 0, 0, 0. We expect that both point distribution to have a mean close to 1.1.1. However, unexpectedly, the red points show less MAC error than the gray point because the red point tends to be dense, reducing the variance. So, we can view that applying James' line estimator is to balance the bias and variance between path trace results and the denoise results. Here is the figure showing that the combined results show lower error and better visual performance than the inputs. This work used a simple unit to estimate the combining parameters of the James-Stein combiner, naming it a neural James-Stein combiner. The trained neural James-Stein combiner works on ridiculous cases like this simple box filters. This simple box filters show very blurry artifacts, but once it is combined with the path trace results, it enhances the final visual results. Here we can see that the combined results, the red lines, outperform the two inputs on all noise levels. And this work can be also applied on any unbiased and biased method pairs, like the bidirectional path tracing and photo mapping, the SPPM, like this figure. So, thanks for following, and this is what I have covered for this lecture. So I hope that this lecture helped you understand recent topics in Monte Carlo noise reduction and to develop your projects. Any questions are welcome through email or through KLMS board, or you can come to my office. Good luck with your midterm exams, and bye!